everybody. I'm really happy to be here today to share with you what I did over the past 4 years here with the help of my advisors, Delaire and Delaire. So the overarching question of my dissertation work was how to improve access to safe water in West Bengal, India. And there are several aspects to this question, from arsenic and bacteria removal to household behavior change. And today I want to walk you through all of these aspects. So let me start by giving you a broad overview of the arsenic problem. As you can see, arsenic in groundwater is a worldwide problem. I'm showing you a map of the probability of arsenic in groundwater. And yellow spots indicate low-risk zones, and red spots indicate high-risk zones. So what should strike you is that arsenic in groundwater is really all over the globe, and I should say that most of these high-risk areas have been confirmed with actual measurements. And today I want to focus on this region because this is one of the most populated areas in the world. So South Asia, as you can see, is really at high risk of groundwater contamination, and this is a real cause for concern because in this region, rural communities rely heavily on groundwater for drinking. So this has not always been the case. Before the 70s, these rural communities relied on surface water, which is ponds or rivers, for their drinking needs. But starting in the 70s, the World Health Organization and UNICEF pushed and sponsored the construction of millions of hand pump wells for people to switch to groundwater. And this was done as a way to protect people from contaminated surface water, ponds with heavy fecal contamination. And this was done as a way to reduce childhood mortality due to diarrheal disease. Unfortunately, about 10 years or 15 years in, a researcher in West Bengal, India, found arsenic in groundwater. And soon after, it was also found in Bangladesh, in Vietnam, in Cambodia, in China, in other states of India. And today it is estimated that 55 to 60 million people in South Asia are exposed to this contaminant. So we're talking about massive scale problem. So how did arsenic get there in the first place? Well, it turns out arsenic is naturally present in the iron oxides minerals in the ground, in the subsurface. It is literally trapped in the rocks in the subsurface. And when groundwater is rich in organic matter, bacteria that grow on this organic matter quickly deplete the groundwater from oxygen. And when they run out of oxygen, they need to find something else as their electron acceptor. And they soon start to use iron oxide solid minerals as their electron acceptor. And that leads to the dissolution of these iron oxide minerals. And as a result, arsenic that was trapped inside is able to leach out. So this results in a layer of groundwater being contaminated with arsenic. And this layer is approximately, in the region, 50 to 200 feet deep. Above that layer, anoxic conditions never develop. There is still enough oxygen. And below that layer, there is not enough organic matter to foster bacterial growth. And this is quite unfortunate because this depth is where most of the hand pump tube wells are tapping into. So the World Health Organization recommends a maximum contaminant level of 10 microgram per liter. And it is not infrequent in this region to find levels as high as not always as high as 4,000 microgram per liter, but 500, 600 is quite common. So arsenic over the long term builds up in the body, and over several years it leads to a number of negative health impacts, such as skin lesions and dots on the palms and feet, gangrene, a lot of internal cancers, cardiovascular diseases, lower IQ in children, and premature death. And the World Bank estimated about 10 years ago that there were already 700,000 arsenic patients, so people with visible and diagnosed symptoms. So again, a massive scale problem. So I want to focus on West Bengal, India, which is one of the affected areas, and give you a precise overview of the situation here. So rural West Bengal is a very populated area, 62 million people, living in very poor conditions. 25% of this population lives below the poverty line. And they use groundwater as their primary water source. And it's important to keep in mind that groundwater is a very convenient source of water. It is located on the premises, on the plot, or really near the plot. It is free and it is abundant. But it contains, like I said, arsenic, which is an invisible contaminant with very long-term health effects. So this makes it really hard to raise awareness on the issue. But arsenic does not come alone. Often arsenic-contaminated groundwater also contains high levels of iron. Remember, the same mechanism that leads to the release of arsenic also leads to the release of iron. So iron is very unpleasant. It gives a weird taste and a weird color to water. There is usually rust in water and in the water containers such as this. And finally, this region is fairly poor and has inadequate sanitation. About 40 to 50% of people still practice open defecation. And when latrines are present, they're, like on the picture, located near the water source. And so it's fair to say that groundwater is at risk of having some fecal contamination as well. So this is a broad overview of the water situation. So here is a vision, one possible approach to address the problem. So I'm going to read it to you. The vision is to treat groundwater at very low cost in village-scale treatment plants that can sustain themselves financially by selling water to households. Okay, so this is a long vision. I'm going to break it down for you into 3 different parts that rely on different assumptions. The first assumption, the first hypothesis, is that we can indeed treat this groundwater, remove arsenic, iron, and microbes at very low cost. And probably to do that at very low cost, it would be better to do it all at once. Then the second hypothesis is that we can do this in a village-scale treatment plant, so locally, and the process therefore should be simple, easy to operate, no hazardous material, and it should rely on local supplies and consumables. The third hypothesis, in blue, is that people are willing to purchase treated water. And then the fourth hypothesis is kind of the overarching hypothesis, is that if this vision can be realized, then the problem can be solved. And which raises the question, how much of the problem can this approach actually solve? And so we'll come to that at the end. When I joined the Gadville group, the team had already done a lot of work on this path, and they had developed a technology which is called iron electrocoagulation, and I'll come to that, which met all the criteria for being applicable in low resource settings, and which removed arsenic and iron very effectively. And my contribution to the team was to look at the remaining parts of the puzzle. So this leads me to the outline of this presentation. First, I will present iron electrocoagulation, this technology I was talking about. And mainly my goal is to convince you that it can remove arsenic effectively. Then I will move on to the first part of my contribution, which was to look at how the same technology can remove attenuate bacteria. Then I'll move on to the second part of my work, which was in social sciences, looking at household behavior change in West Bengal. And I'll conclude with some recommendations. All right, so this is a picture, a simplified vision of what iron electrocoagulation looks like. So very simply, we have 2 iron electrodes immersed in contaminated water. So you can see arsenic in this water. And then a voltage is applied between the 2 electrodes. And this results in the anode dissolving and producing iron 2. Iron 2 quickly oxidizes in the presence of oxygen to form iron 3. And iron 3 is very soluble at circumneutral pH, so it immediately precipitates and forms these small iron oxide precipitates, literally small rust particles. And this is very fortunate because arsenic has a really high absorption affinity for these rust precipitates, and so arsenic is removed by absorption. A second concurrent process is during iron 2 oxidation, some strong oxidants are produced, for example, iron 4, which can convert arsenic 3 into arsenic 5, which is easier to remove. So we have these 2 processes at the same time. And after a settling period, all the sludge is collected at the bottom, and the upper water is safe. So this process is really appealing because iron plates are widely available everywhere, including India. Electricity can be found at least in one spot in each village, not in every household for sure, but it's not impossible to have electricity in at least one point in a village. It's simple to operate. There is no media to be backwashed, no media regeneration, so no hazardous chemicals involved. And this process was actually piloted during a 3-month field trial in West Bengal, India in 2012. It was a 600-liter prototype operating in a rural school. And what we found is that very little sludge is produced. I think it was estimated about 1 gram of sludge per gallon of water treated, so it's fairly small. It is very effective. Here I'm showing you post-treatment arsenic concentrations over 1 month of operation. And you can see we're way below the WHO maximum contaminant limit consistently, even though initial concentrations were 250 to 300 microgram per liter. And finally, it is a fairly low-cost process. So during this field trial, amortized capital cost and consumable cost were estimated to be about $1 per cubic meter, so it's encouraging. All right. So now I want to move on to my investigation of whether this technology can also attenuate bacteria. And if so, what are the mechanisms? How does it attenuate bacteria? And finally, the third question guiding this part is, what is this process vulnerable to? Is it sensitive to the water composition, to the type of bacteria? What can we learn about how robust the process is? So when you want to answer a question like that, you're back to the lab. You're back to a very easy, controlled, simple experiment, back from the 600-liter prototype to a 200 ml beaker, 2 small electrodes immersed in it, and a pH probe to control pH. I added synthetic Bengal groundwater, which is a mix of ions that are supposed to mimic arsenic-contaminated groundwater over there, and it includes arsenic. I added E. coli, which is a model bacteria, gram-negative bacteria that is very similar to a lot of enteric pathogens, and it's commonly used in drinking water treatment experiments. And then the 2 electrodes get hooked up to a power supply, and just before turning on the current, I take a sample to enumerate bacteria. Then the current starts, rust particles, precipitates start to form, and it's very visible. There's actual rust in the beaker. And after a settling period, during which all the sludge accumulates at the bottom, there is this settling, And after settling, we take a sample from the supernatant, again, to measure post-treatment bacteria concentrations. And so the way bacteria are enumerated is by putting a small amount of sample on growth media, and after overnight incubation, you can count colonies. And that's how you count man-made bacteria. So in drinking water treatment, bacteria attenuation is calculated in terms of log. So 1 log is 90% attenuation, 2 log 99%, etc. And so here I'm showing you E. coli attenuation as a function of the iron dosage. So how much iron we put in the system. And what you can see is if you're dosing enough, you reach 4 log attenuation, which is the WHO recommendation for household water treatment. So we do get sufficient treatment. And what's really interesting is that at the same time, we're removing arsenic down to below 10 micrograms per liter. So we do have a technology that can remove both bacteria and arsenic at the same time, which is exactly what we wanted. Okay, so this is where the science starts. We know it works, but we still don't know how. And so the rest of my work was to dive into the mechanisms of this attenuation. And really, 2 things could be happening to end this process. Like I mentioned earlier, the oxidation of iron 2 produces strong oxidants that can cause oxidative stress on bacteria membranes and kill them. So that's called inactivation. You're killing bacteria. The second process could be that bacteria get trapped and agglomerated in those within those rust particles, and then be removed by settling. And so we don't know if it's removal of inactivation. One way to find out, so there are 2 methods that I use to find out. The first one is to compare iron electrocoagulation, which I will call iron EC from now on, with coagulation by iron 3 salt. So iron 3 salt will produce the same precipitates without going through the iron 2 step, so with no inactivation possible. And so what I found is that iron EC really leads to similar levels of attenuation as an iron 3 salt, which means it behaves as though there was no iron 2 in the process, and this suggests that there is very little inactivation. And this could be confirmed using a second method, which is called light staining. So in this method, you stain bacteria, and they show up with different colors on the fluorescent microscope. They show up as green, so individual green cells indicate live bacteria with intact membranes, whereas red cells indicate dead bacteria. And so there are overwhelmingly more green cells, which confirms that the main mechanism is removal. So bacteria get removed within the flux of rust precipitates. And we can see that these pictures kind of show that in the background. The shape that you see behind these individual cells is actually a big flock of precipitates. And if we zoom in using transmission electron microscopy, what we can see is that actually small individual precipitates adhere on the surface of bacteria and bridge between cells in a way that ends up trapping them in those big networks. And so really, this picture motivated the rest of my research. The question is, what is going on here? How come precipitates appear on the surface of bacteria? What type of interactions are we looking at? So the first question is, how important are electrostatic interactions? Are we looking at electrostatic mechanisms or something more specific? So to look at that, I changed the ionic strength of the solution over several orders of magnitude without seeing much of a difference on E. coli removal, which suggests that electrostatic interactions are not a big part of the picture. They don't play a major role. And instead, we're looking for much more specific interactions between precipitates that would interact chemically with bacterial surfaces. And so it's useful to start thinking of what a bacterial surface is really. So for our purposes, a bacteria is a surface with 4 types of functional groups: amine groups, carboxyl groups, phosphate groups, and hydroxyl groups. So we can already kind of rule out amine groups and hydroxyl groups because none of them have a very strong specific affinity for iron oxides. However, both carboxyl and phosphate groups do have specific affinity for iron oxides, and they're good potential candidates for having specific interactions. So we're going to find out. So one way to test this hypothesis, so again we have carboxyl and phosphate groups on the surface of bacteria. One way to test if they're involved or play any role is to complex them using bivalent cations and see if it interferes with the binding of precipitates. And so I use calcium and magnesium because they're known to bind to these groups, but also they're environmentally relevant. They're often present in large quantities in groundwater. So it was also interesting to know how they would affect the process. So using constants, absorption constants and acidity constants from the literature, I was able to calculate the amount of bacterial surface groups complex for each concentration of calcium. And you can see that if you're increasing the calcium concentration enough, you get to about 70 to 90% complexation of those carboxyl and phosphate groups. So this is from a very simple equilibrium model, but I could confirm that surface groups were being complex by measuring the surface charge of bacteria, or their zeta potential. And we can see here that the zeta potential increases as the calcium concentration increases, which is consistent with positively charged ions complexing negatively charged groups. All right, so how does this affect bacteria attenuation? Well, this plot shows you that E. coli attenuation drops by about 1 or 1.5 log as the calcium concentration increases. And the same behavior was observed for magnesium even more significantly. And so really this set of results is consistent, supports that precipitates interact directly in specific interactions with carboxyl and or phosphate groups. So at this point, we don't know which one of these groups, if both, play a role in the process. And my approach was to use competitors. So phosphate and silicates, which are also present in groundwater, can act as competitors because they can absorb onto iron oxides. And phosphate is a much stronger competitor than silicate. So here I'm showing you E. coli log attenuation without any competitors, with silicate competitors, which didn't have any effect, and with the stronger phosphate competitor. So this is the results for E. coli cells, and we want to compare that with the behavior of carboxyl and phosphate groups individually. So let me explain. These experiments here, 2 and 3, did not involve any bacteria. I just used, in this case, citrate as a proxy for carboxyl groups, and here phosphate as a proxy for phosphate groups. And I'm looking at how competitors interfere or affect the absorption of these groups on iron oxides. And so if you just quickly look at these 3 graphs and compare them, you should see that the bacteria graph looks a lot more similar than the phosphate graphs, and not so much similarly to the carboxyl graph. Specifically here, silicate had an effect on the absorption of carboxyl groups, whereas it did not on the absorption of phosphate or on the removal of bacteria. So this is important because it tells us that if carboxyl groups on bacteria were playing an important role in the adhesion process, if they were a primary site for the adhesion of precipitates, then silicate would have had an effect on bacterial removal because silicate interferes with the absorption of carboxyl groups. But instead, silicate had no notable effect on bacteria attenuation, and therefore we can conclude that carboxyl groups are really not a primary adsorption site for precipitates, and instead phosphate are the main site. So here's what we know so far. Phosphate bacterial groups are the primary site for the adhesion of precipitates, and we know that therefore phosphate in water will strongly compete. So all of that is summarized here with these two columns. We also know that calcium and magnesium affect the process by complexing the bacterial groups. But what we know from the literature is that calcium and magnesium can complex this adsorbed phosphate. And when we talked about before, is that they can also bind with bacterial groups. And so it would be interesting to know if these bivalent cations can bridge between precipitates and bacteria when competitors are present. And so I did experiments looking at phosphate inhibition in the presence of calcium and magnesium. And what you can see is that when these bivalent cations are present, phosphate no longer inhibits or interferes with adhesion, which supports this bridging mechanism. So overall, we learned that precipitates interact specifically with phosphate bacterial groups, either directly or through bivalent cation bridging. And so in addition to being fascinating, this mechanism is really useful because it can help us find out how different ions, or whether natural organic matter or different bacteria types affect the process. So really for ions, we already answered the question, and at the same time we know that bivalent cations such as calcium, magnesium, or others are going to decrease removal. We know that silicate and therefore other weakly adsorbing ions, other weak competitors do not affect the process. However, phosphate and other strong competitors will affect the process, such as, for example, arsenic 5, unless bivalent cations are present, in which case they don't have an effect. So we kind of already sorted out the ion part of the problem. Now we can look at natural organic matter. Natural organic matter are big organic molecules that are the residue of biodegradation processes, and they are usually found to interfere with water treatment mechanisms. And here, what I did experiments, so I should say, natural organic matter is not present in very large quantities in groundwater, but like I said, arsenic develops or is released in areas rich in organic matter, so it's not uncommon to see up to 3 or 5 milligrams per liter of NOM. And so I did experiments using 3 milligrams per liter of Suwannee River fulvic acid, which is one type of NOM. And what I found is that NOM really did not impact much the process, right? The difference is within the error bars. And when you think about it, it's not that surprising now that we understand mechanisms. The surface groups, or the functional groups on NOM, are mostly carboxyl and hydroxyl groups. None of them are expected to interfere with phosphate groups. So it makes total sense that NOM does not have a big effect. What about bacteria type? Well, you may know that bacteria have different categories with different surface characteristics. We have typical gram-negative bacteria. Some of these gram-negative bacteria have short lipopolysaccharides, and then we have gram-positive bacteria. And I wanted to know how are different bacteria removed. And again, using different bacteria, we see that attenuation is not really different for all these bacteria. And again, it's not that surprising because even though all these bacteria have very different microscopic compositions on their surface, the same functional groups are present on all of them. Carboxyl, phosphate groups are present on all of them in about equal amounts. So if phosphate groups are present everywhere, it's not so surprising that all bacteria would be removed similarly. All right, so that concludes this first part about bacteria attenuation. To summarize, we learned that iron electrocoagulation can remove bacteria and arsenic simultaneously. We also know that the mechanism is that precipitates interact specifically with bacterial phosphate groups and therefore adhere to the surface of bacterial cells. And this allowed us to understand why some water components would affect the process a lot when some other do not. So if you wanted to, I think we should go look into this a little bit more to validate the results in the field with real groundwater and real actual pathogens in the field, and also no work or very little work has been done so far with viruses. So it would be very important to check that, because viruses have a much lower infection dose, so it's even more important to be removing viruses in addition to bacteria. Okay, so now we can move on to the second part of my work, which was about household behavior change. And just so to remind you, the questions are: is there demand for purchased water, for treated water in West Bengal, India? Are there other options other than purchased water? And if so, do they compete? What are the main drivers for using these alternatives? What are the motivations for people for doing that? And finally, we'll finish with this question: is purchased water enough to solve the problem, or how much of the problem can it solve? So this part of the work relied on a very different approach. I conducted a survey in West Bengal, India, in a rural region located about 150 miles north of Kolkata. And in this area, again, people use hand-pump tube wells, private tube wells located in front of their house. And I chose this area because groundwater has high levels of arsenic, and I could confirm that it also has high levels of iron, and I believe some people contamination. So the reason why I chose this specific area, or these specific villages where I worked in, is because they had already some alternatives to contaminated private tube wells. One of these alternatives was purchased water. So it was very interesting. It was a water entrepreneur in the village itself had built this small treatment plant in his house and was producing 20-liter jars of treated water and distributing it to the surrounding area. So a business model really similar to what we envisioned. A second option that I found were domestic filters. So people were filtering their water at home, either in filters that they build themselves using sand and gravel in a ceramic pot, for example, or using purchased filter. A third option, so both of these are not free, right? You have to either pay for purchased water or pay for your filter. Another option, which was free, were government tube wells. So the government sometimes comes in and builds deeper tube wells than the private ones. They're supposed to go as deep as it's required to hit the arsenic safe water. They don't always do, but let's pretend they do. They're a little bit deeper, and so they have also less iron, and visually it looks safer. And finally, a fourth option that was available in one of my study villages was piped water. So piped water then has nothing to do with the piped water you're used to. We're talking about a few stand posts in the village that deliver intermittent water. So for example, 3 hours in the morning, 3 hours in the afternoon, and you have to line up with your buckets to fill it. But it's quite popular though because it looks cleaner than private tube wells and it's free. So my approach was to conduct a household survey with the help of 4 amazing Bengali surveyors. So here I'm showing you a few pictures of what it is to do a household survey in a rural area of India. And so we literally went one every four households to interview people. And we asked a bunch of questions about the water sources that people were drinking from and how frequently they were doing so. And then we evaluated 13 potential explanatory variables. So let me explain the jargon. An explanatory variable is a factor that may affect your outcome. In this case, the use of alternatives to private tube wells. And so these potential variables, explanatory variables, have to do with socioeconomic status, risk perception of arsenic, iron, gastric illness, social influences, for example, whether the woman goes to a women's group, whether people receive advice about water from their doctor, this type of the behavior of their peers, this type of social influence. The perceived quality of alternatives, whether people think purchased water looks safe, tastes good, is also potentially important. And then we looked at other factors such as aspirations or the presence of young children. So the first question is there demand for purchased water? It's quite easy to answer just by looking at the breakdown of water behaviors. So I'm showing you results from my first survey area where we surveyed 409 households, and this area had no piped water. So you can see that about 25% in blue, 25% of the households were using purchased water. About the same amount of people were using other alternatives, domestic filters or government tube wells. And then about half of the people were not using any alternative at all. Then for area 2, the second area where I worked, where I sampled 92 households, this area had piped water. And so quite interestingly, before piped water arrived in the village, about the same amount of people were purchasing water, 24 versus 25, really the same amount. But after piped water arrived in these public standboats, purchased water almost died, ran out of business, and everybody switched to piped water. So is there a demand for purchased water? Sure, there is demand, but there is also the same amount of demand for other alternatives. And finally, when piped water comes in, purchased water is out of business. So those are the main important qualitative findings. Now, a very interesting question is what drives households to use alternatives? And so I'm going to first introduce you to those results using principal component analysis, which is a statistical tool that looks for correlations between variables. And so what it does is it looks for dimensions into these factors that are not correlated at all, which become the y and the x-axis, and then it plots all the factors of this plot so that you can easily see what's correlated and what's not. So here, what you should see is that the use of alternatives is correlated to both socioeconomic variables and risk perception factors regarding iron and gastric illness. And if we look at purchased water individually, we have sort of the same picture with less of an influence of socioeconomic status, and we can see that the perceived quality of purchased water now becomes correlated. So this is the first broad overview to start thinking of what the main drivers are. But of course, all of this can be confirmed with more robust statistical tools, such as fully adjusted regressions. So here I'm presenting you the results of regressions where 13 explanatory variables were included in the regression. And I'm just showing you numbers for factors that were statistically significant. The asterisks represent significance, and the numbers represent the weight of the factor in the behavior. So if we're looking at the use of any alternative, filters, government tube wells, or purchased water, we see that 4 factors are main predictors: socioeconomic status, risk perception of gastric illness, and just behind, the satisfaction with iron and arsenic knowledge. If we look at purchased water individually, we can see 2 other factors pop up: doctor's advice and the perceived quality of purchased water. And then we can do that for all the alternatives. So we're not going to look at the numbers in details. I just want to give you some big, key points and key take-home messages. The first one is that socioeconomic status is the main predictor for the use of any paying alternatives. So purchased water, domestic filters, makes sense. The second main finding is that the risk perception of gastric illness is a major predictor all across the board. It seems to be a primary motivator, no matter what the alternative. And it is also a stronger predictor than arsenic knowledge, which was smaller in weight or not even present in some cases. And then finally, it's important to recognize that the perceived quality, the taste, the smell of water is also an important driver for piped and purchased water. Okay, so that's what generally drives people to use alternatives. But what about who chooses filters versus purchased water versus government tube well? How is this competition taking place? And so to look at that, I did the same type of statistical analysis, but really the results can be summarized in this easy plot. On the y-axis, socioeconomic status favors domestic filters and purchased water, and on the x-axis, participation in women's group was found to favor purchased water. And so the take-home is that government tube wells are used by the poorest households. But if you compare filters versus purchased water, there's a real difference in socioeconomic status. In fact, those 2 alternatives compete at any level of socioeconomic status. Also, there is no difference in risk perception factors between filters and purchased water. The only difference we found was relative to social influences. So women's group, external advice, where people received advice from the doctor. That's what seems to favor purchased water, but not risk perception indicators. So there are a bunch of implications of these findings. So remember, the first motivation was, okay, we have some demand for purchased water, but can we increase it? Can we increase that number? Well, sure, we probably can. We understand that after socioeconomic indicators, risk perception factors are the primary motivation. And within them, we know that salient problems such as gastric illness, iron, things that you can readily see or you experience consequences of the next morning, are much more important drivers than arsenic knowledge, which is an invisible long-term contaminant. And so this finding is not very surprising. It's quite intuitive. Salient problems are more important to drive decisions than invisible pollutants. But I think it's important to remember that therefore, raising arsenic awareness may not be the most effective lever to increase adoption. In fact, raising awareness about gastric illness is going to give you better results. So that's one thing to keep in mind. And in a way, that's not such bad news. Raising arsenic awareness is really hard. It's really slow because, again, it's invisible. And it's also very related to wealth and socioeconomic status. I'm taking you back to the principal component analysis. Arsenic knowledge is directly correlated with socioeconomic status, whereas the other risk perception factors, iron and gastric illness, are a lot more widely, broadly shared and have nothing to do, they're uncorrelated to socioeconomic status. So it's actually good news. We have a lever that's more effective than arsenic knowledge, which was highly unfair and inequitable. The second implication, I think it's a good lesson for researchers or practitioners who always tend to think that what they think as the biggest priority, in this case arsenic, is not necessarily felt as the biggest necessity by the local people. And we need to remember that if we frame our discourse to acknowledge all problems experienced, in this case iron, gastric problems, and arsenic, we make it much more relevant to people. The second implication, if we manage to increase adoption of purchased water, we're probably going to increase adoption of the other alternatives as well, because again, there's no difference. People don't choose these alternatives based on risk perception. So everything's going to go up. And this could be a problem, because governmental wells are not always deep enough, and domestic filters are not always designed to remove arsenic. And so we need to keep in mind that these behavior change strategies are also going to increase the adoption of technologies that don't necessarily work. So we need to be aware of that. So now I'd like to go back by my, critical thinking question. How much of the problem can purchased water address? And to answer this question, I would like to draw your attention to these results about the consistency of use. Because purchasing water doesn't mean that you're always drinking purchased water. In fact, a fraction of people are using purchased water only when they're sick, or only when they have guests or celebrations. In a number of households, just the layer above, purchased water is only used by some members, but not all. And then in some households, in light blue, people drink purchased water or private tube water intermittently, with no real reason. And then only a fraction of people, the pink people, exclusively drink purchased water. And so there's literally a ladder of behavior change, and it's important to be aware of that. And an important finding is that filters and piped water are generally used much more consistently than purchased water, for example. And when I analyzed what predicts where people are on this ladder of behavior change, the only factor that predicts how high you are on the consistency graph is socioeconomic status. And so if we want to rate or grade these different alternatives, purchased water rates pretty poorly in terms of consistency of use, just like government tube wells as well. And in terms of equity, I would say it rates even more poorly than domestic filters, because not only the use of purchased water is driven by socioeconomic status, but now even the consistency of use. So really, in this case, we can compare them this way. Then we asked if people were using these alternatives for cooking, and only domestic filters and piped water were used for cooking as well. So according to these metrics, really, purchased water now looks pretty bad, right? So I really now want to remind you why in the first place we thought it was a good idea. So first of all, we think this model of treating water in small treatment plants is much more likely to succeed at removing arsenic in the long term. Like I said, government tube wells are rarely deep enough. It's very frequent. In fact, in the village, I tested them. They were not arsenic safe. domestic filters, even if they were in the beginning designed to remove arsenic, it's really impossible for a household to know when the media needs to be changed. And there is no system to replace the media, even if they wanted to. So really there is a strong preference for the model of treating water at the micro-utility scale is much more likely to succeed to protect people's health. And then if we compare purchased water with piped water, well, purchased water has a cost recovery mechanism, which makes it much more likely to be financially sustainable and scalable. So I just wanted to put that in the balance. So overall, what's the best option, right? All of this is quite puzzling. Well, my opinion is that purchased water is probably the most promising solution in the short term. Piped water is slow to come. The government is really slow to bring piped water. It costs a lot of money, and the reason is there is no cost recovery in place. People are not paying for it, so it's really hard to fund the capital costs and maintenance costs. The purchased water model that we envision is much more scalable and financially sustainable, potentially. So it's probably the best short-term option. But we need to be aware that there are a number of limitations. The first one is equity of access. We talked about it. It really favors higher socioeconomic status households, and we need to be aware of that. And then the second limitation is from the perspective of the water entrepreneur himself. Remember, the day piped water comes in, even though before he was doing a decent business, the day piped water comes in, he's pretty much out of the picture. And so we need to be aware of this tension, because if we're going to recommend that small treatment plants are built in villages, we need to know that these people are going to be very, very vulnerable the day the government comes. So it's important. Actually, currently in West Bengal, if I'm correct, both the Public Health Engineering Department supports piped water, and the government of West Bengal now said that they want to promote the construction of purchased water treatment systems. So you can see the inconsistency because they're going to shoot themselves in the foot. So it's interesting to be aware of the tension. None of them is perfect, but there's definitely a tension. So I want to finish by going back to this initial vision. Treat groundwater at very low cost and sell it in financially sustainable plants. So we dealt with objective one, almost. We know that we have a technology that can remove arsenic and bacteria. We still don't really know for viruses, but we're optimistic. Then, regarding objective two, we're pretty confident that this technology can work in a low-income setting. But like I mentioned, or like I did not mention, sorry, what makes the water entrepreneur less vulnerable to the installation of piped water is if the price of purchased water could drop. So really, it's on us, on researchers, to make this price drop, to make them more resilient in the face of piped water coming in. So how low can the price be is definitely a challenge. We now understand the levers of behavior change, what motivates or drives people to change their behaviors. And in terms of the fourth objective we're looking at, we now understand the limitations of this vision, which are mainly in terms of equity of access and possible vulnerability to the installation of piped water. And again, we can really not eradicate these limitations, but we can possibly minimize them by lowering the cost of treatment. With that, I would like to thank a lot of people, a lot of whom are here in this room. First of all, my advisors, Bishop Gadville, thank you for showing me how to do purposeful research. I want to thank Kara for supporting me with a lot of technical advice. And I want to thank Isha Ray, professor in the Energy and Resources Group, who accepted a few years ago to advise me on my social science project. I really don't know why she accepted, but I'm really grateful she did, because it was really incredible to work with her. I want to thank a lot of people in my department for all their technical support, analyzing data, understanding methods, getting equipment. I couldn't have done this without them. I want to thank Case, who is my other advisor, former PhD student in my group. I want also to thank my survey team in India, who was awesome, and all the people who helped me in this journey. And I also want to thank my funding sources.
Final questions?
Yeah.
Are you familiar with whether there is hard water in these areas and whether ECAR has to be optimized for calcium and magnesium in these waters? Is that something you've looked into?
Yeah, water is definitely hard, but it's actually, so it was not such a good thing for bacteria removal, but it's a great thing for arsenic removal.
Okay.
Calcium helps in the removal of arsenic, so we don't think that we need to pre-treat it. It's actually pretty good.
In this electrocoagulation process,
Yeah,
you're producing some solids itself.
yeah,
So you've got a sludge that's at the bottom that's rich in arsenic,
yeah,
entering bacteria.
yeah.
What are your recommendations for disposal of it?
Yeah, so I think it's a great question. It's actually the one area of research that could be where we can make the most progress right now. Fortunately, the amount of sludge is small compared to if you had to dispose of an entire field for urea. One possible, so drying the sludge would probably kill the bacteria if we do it at sufficient heat. Right now, one approach is to incorporate the sludge into concrete or cement because iron is already part of the recipe for this. So there is another researcher at another university looking at how we can incorporate it in building materials. I should say one of the main challenges is not so much what we're going to do with the sludge, is how we're going to collect it. Because imagine 6,000 villages where you have this little bit amount of sludge that you have to collect. It's a logistical challenge a lot more than a scientific one. Yeah.
So do you have reason to believe that the piped water is safe? So it's surface water and then it's disinfected or something?
Yeah, in this study area, it was surface water that was chlorinated, so it was quite simple. I do think it's safer than groundwater, for sure. Now, is it completely pathogen-free? I don't think so, because the way people connect themselves to the main pipe is they're doing their homemade connection. There's probably tons of leaks and tons of contamination. But if I had to choose between iron, I believe, water, and pipe water, I would probably take the pipe water. So people really prefer it because of the color. It looks like normal water, whereas tuba water is not.
But if you're trying to think about this from, like, say you're advising, the agencies of West Bengal about, the government agencies about what is going to be the most sustainable long-term approach to protect public health. Is it small scale
Treatment plants or purchased water. Well, my personal thinking is that small treatment plants selling water is a better option because I think they can remove, there's less risk of contamination in the process, but I also know it's not going to serve the poorest of the poor. And so I don't know what's a good strategy. Is it cross-subsidies? What should we do to protect the health of everyone? Because a big feature of piped water is that everyone uses it independent of socioeconomic status. So there's this appeal in terms of equity. But I do not think that at the moment the government of West Bengal has the political will to actually scale it up. It's just not happening. It's just a chance that it was there in this village, but all the other villages don't have it. So, yeah. Right?
Do you have a sense of how you will choose the village in this water? Where that will get in terms of
Yeah, I have a sense that it's highly political. It's actually heartbreaking. Like the first area where I worked, they've been waiting and promised pipewater for about 5 years, and the tower's been built to deliver it. And when we visited the tower, it's completely, out of use. Clearly there was some legal issue or some complication with the contractor. Instead, they put it in another village. I'm not sure how they choose. It was also really hard to talk with government officials because they tend to deny all the problems that are going on. Or we were like, are you aware that there are small treatment plants working in these villages selling water? No, we don't have any such business. Water is free here. Okay. Everybody's buying water all over the place, but let's forget it. So yeah, I think it's a very political process. Yeah.
I know this is outside of your field of expertise, but have you been able to think through how your household level analysis informs government in terms of long-term planning, like for larger socioeconomic phenomena like climate change and rural to urban migration. So if they're going to put in a piped water system, which is kind of a sort of a locking situation, how does your household survey help to inform governments on that?
Like you're asking, is the government prioritizing some areas depending on the socioeconomic characteristics?
In terms of advising the government and agencies on what to put in as one of the factors of should they put in piped in water systems or should they continue on with more temporary type of business?
Yeah, well, the government so far is not responsible for these businesses. Those are like spontaneous offshoots, people who are doing their business. Well, if I had to recommend them, I would say, I would probably prioritize a number of villages that are really low income. There is a number of tribal communities that are really, really poor. So probably those should have piped water because it's likely that purchased water and bottle will not work. But then I would also recommend the government not to promote these water entrepreneurs in places where they're going to bring piped water the next year because they're going to kill their business. So really, I feel unqualified to recommend the government over Bengal. I can just say what how this vision that we had and how far it can go and how we need to work. James.
Great talk, by the way. I was wondering what kind of current efficiencies are you getting in eCar?
Like
Yeah.
the faradic efficiency, we're getting really high efficiencies in the, okay, good question. The lab are really good. We get 95%. We don't have much oxygen evolution on the electrode. Now, in the field, we're not sure because we've never been able to measure iron in the field. It's actually quite hard in a very large reactor that's not well mixed to take a sample and say, oh, this is the iron concentration, because there is no such thing as the iron concentration. So we do see decreased efficiency or arsenic removal in the field. It could be due to less faradic efficiency, but we haven't figured it out yet.
And do you know if there's any chloride in the groundwater at all?
There's chloride. There's
Have you thought about potentially the oxidation of chloride to chlorine
Yeah,
as a potential inactivation?
yeah, so it's a good question. So I compared iron electric regulation to an iron 3 salt. I also did the same work with an iron 2 salt, and we also have the same attenuation. So if there was some additional inactivation due to chlorine, we would have a discrepancy between iron 2 salts and iron C, which we didn't. So I don't think there is much of that.
Okay.
Hi, thanks. Do you have a sense of what other cultures around the world your survey might inform in terms of how people behave at their water collection? You showed the map, arsenic's a problem everywhere.
Yeah. So I think the survey results can apply to any area that has a visible contaminant, in this case iron, together with the invisible. And when I showed the map of the world, not all of these regions have iron together with arsenic, because the process I presented of reductive dissolution of iron oxides only applies in parts of these high-risk areas. In places such as California or Latin America, the arsenic mobilization mechanism is different. It's from high pH dissolution of rocks. So there will be no iron, no visible convenient stuff that goes with arsenic. So I don't think, for example, in these places, the result. But I would say probably in the rest of South Asia, where iron is present, thank God there is something visible with arsenic that people want to run away from. Yeah.
I'm curious to hear about the role of pH in the kinetics or the removal mechanisms in the process, because I feel like when you're trying to treat different groundwaters all over the world or all over the country, you're going to have different influent groundwater conditions.
Yeah, so it's a good question. The main thing that pH controls in this process is the rate of oxidation of iron 2. Iron 2 remains a lot longer in the system when the pH is 1 unit lower. For example, it's at 6.5 instead of 7.5. And what I found is that there is higher attenuation at lower pH, and we investigated why that was, and it turns out that there is some iron 2 remaining in the supernatant during settling,
which leads to the inactivation of bacteria during settling. So there is, I said, removal is the main mechanism. Well, at lower pH, we also have an additional participation of inactivation. But I should also say, in real applications, when you pump groundwater, even if initially it's at pH 6 or 6.5, it's unlikely to stay there. It's going to equilibrate with the atmosphere. CO2 is going to go out, so the pH is probably going to increase to a point where inactivation doesn't matter.
Can I know?
Yeah, sure.
You described the mechanism of removal of bacteria
Yeah.
almost completely to electrostatic mechanism. How much influence do you think is just physical entrapment in the iron hydroxide precipitated form?
Right. So I actually don't think that electrostatic interactions play a big role. I think we're talking about, it's not like the negative charge being attracted to a positive charge. I think iron oxides actually form chemical bonds or interact much more closely than that in phosphate groups. Phosphate and iron oxide have very strong affinities, and this is what's happening on the surface. So that results in small precipitates adhering on the surface of bacteria, and then it bridges between different cells, and in the end, bacteria are trapped into the big blocks, like you said. So on the surface, it's a very specific chemical interaction, but macroscopically, it's just bacteria trapped in an iron oxide block. Yeah.
I thought your graph of the use of multiple sources was really interesting. And
Yeah.
I'm wondering, with these pipe systems, if you have any sense of the reliability, especially the seasonal changes in availability, and if that would change demand for other.
Yeah.
Can you repeat your question?
Yoshike is asking if the demand for pipe water or the preference for one versus the other would vary with the season and the availability of different things. So I don't have a sense because I did the survey at one point in time. Also, pipe water had been there for a very short period of time, 6 months to 1 year. So I don't really know. My impression is that I don't think the availability of pipe water will change with the season because it comes from the Bengal River. There is a lot of water there. So I don't expect it to be. I know though that groundwater is really appreciated in the summer because it's very cold. And so this is not statistically significant, this is anecdotal, but people did report liking groundwater more when it's hot outside. My survey was in the winter, so I didn't see that. Yeah.
Okay, thank you.